my cover image, which is a historical structure. And if you look at historical structures, you will see nothing but deep elements, because deep elements work efficiently. They are super easy to design, and you can just use a truss model to design these structures. So this is a very good candidate. If you have no computers and if you have no advanced tools, you can use a strut and tie. You can visualize the flow of forces to understand how the system behaves. Okay. I would say so far you only considered B regions. So this is very common. All right, so I got the focus right. So B region refers to beam region, Bernoulli region, so that is the abbreviation B. And for B regions, you have the typical stress equation, which is based on moment, my divided by moment of inertia, as well as shear stress would be shear force times Q divided by moment of inertia times section thickness, right? So the first one is a very common, it's called engineering beam theory. My colleagues always call this as plane sections remain plane. So that is that one. The second one is parabolic shear strain distribution. It's based on parabolic shear strain distribution in this beam. So, you know, based on this, plane sections remain plane means that you have a stress as well as strain, especially strain distribution, I should say strain distribution, which is linear, something like this, and you have a curvature which is shown by phi. So this is what you are doing for this, as well as if you are looking for shear strain distribution, that distribution is parabolic, which is this one, something like this. Okay, so these are applicable only for B regions. So now let's determine what's B region, what's D region. So let's define first of all disturbed regions. These are called D regions. You might also call them deep region. That also stands for D. That's the right appropriate wording for that one. So this happens if you have sudden changes in geometry. If you have openings, or holes, if you have load application locations, of course every type of structure will have some load application areas. If you have corners, frame joints, supporting areas, which is support reaction location, or bearing plates, any supporting areas qualify for disturbed region. So if you look at the example, you can see loading areas. So I'm loading it from this area, and if the depth is h, right, so typically in order to determine the disturbed region, you need to go h from the edge of the loading plate. So this is going to be h from this way. You also need to go h from the other way, right? So if you do it, you will see these are going to be disturbed regions. That also applies to the load application areas, which is this one, which is H, which is another this one, which is H. So if you look at this system, D regions here. So this is usually a little bit surprising to learners because, you know, pretty much the entire beam ends up being D region. This is also D region. This is also D region. So in terms of B region, we only have this central span as well as this one. So there's really not much in terms of B regions. So the sectional analysis which you do on a daily basis is valid for these locations only. It's not valid for D regions. So I should say these are only valid in B regions. Okay. So I have some space left. My writing is small. I'm guessing you are using that space. So that's intended for participants who has larger fonts than me, which most people will have larger fonts. So if you look at this example, again, you would determine this is H, right? Again, you see the point load. You would go H away. From here, you would go H away. That's the point load application point, H away. It might overlap. So for example, in this shear span, you don't have any B region. So that happens. The entire span is a disturbed region. In this span, this is a longer span, you have some B region. So it's possible you have no B regions on the system, right? In a joint situation, you identify the face of the joint and then go that much this way and then this way for determining D regions. Joint core is always D region, but also H away, you know, call this for example H. This is also D region. A stress distribution sigma would be equal to P divided by area, right? So let's say he's applying force P and this is stress sigma, and that would be the case everywhere, right? So it would be a constant. It's going to be here, same stress. It's going to be here, it's the same stress. So it would have been the same stress everywhere on this section. But if you have a difference between the load application area and the sectional dimensions, there is going to be some stress flow. There is going to be a disturbance, right, for this situation. And let's label this if this is H, right, the disturbance would be H. So this is your disturbed region, again 1-to-1 ratio, So within the disturbed region, you cannot say stress equal to force divided by area, because it is a disturbed region. So you can develop a model for this. So what is happening, what is creating that split is the tension, because whenever you have stress changes direction, so as you can see, stress is coming in this direction. It's like a stress flow. It wants to occupy the entire member. It does eventually, but it needs some distance, which is that distance, which is shown here. Call this h/2, and this is the entire disturbed region, which is h. So the force, you can divide the force into 2, p/2. This is p/2 in this situation, right? And if you call this plate dimension HB, which is this dimension, if you call this HB, this is going to be 1/4 of it. So this is HB/4, right? Which is a quarter of it, which is this distance, 1/4 of the force. And p/2 would change its location. So it's going to come here, p/2, because now you have a uniform stress distribution for this section, which is going to be again p/2 for this. The distance, which is labeled here, is going to be h/4, right? Because this is h/4, it's 1/4 of the entire distance. You can calculate the moment created by this, so let's just do this. This is just a quick hand calculation that we would do. So I'm going to take moment of these two forces. So there's going to be an eccentricity between this one and that one, right, which is this distance, right? It's going to be, so this distance is going to be h/4 minus hb/4. So the moment created based on those two forces would be, this is a couple moment, p/2 h/4 minus hb/4. And you can see these expressions also in the code as well. Okay, so what balances this would be the tension couple, and I'm assuming the tension resultant, which you will see in a minute at this location, I'm assuming tension resultant would be in h/2 location. So this is T, right? This is T at this point. So based on this, I'm going to write here T is going to be p/2 h divided by 4 minus hb divided by 4 and divided to h/2, right? So that's the tension force. So that tension force will come out to be 0.25 p, and you can see this expression in H2 as well, hb divided by h. It depends on the ratio of how wide the plate is as compared to the section depth. So in the wood splitting example, it was an extremely narrow, so he maximized the ratio. His HB was extremely small, so it was just a single point. He introduced the force, and that really amplified the tension, because this second term became almost 0, and he got the maximum tension, which is 0.25 p. So in wood splitting, the maximum bursting tension you are going to be getting if you have the best ratio, which is usually the case because you have a really thin section. That's going to be a quarter of the force, right, for that. So we can do a set and tie model. So a set and tie model is not anything but a rational representation of the forces, right? So if you say this is P over 2, it's going to be a truss model. Truss is, as you know, the basic, the most simple structural model you can have. So this angle, call this angle theta, the angle which makes with vertical axis, and the force would be, two force components would be P over 2, and horizontal component would be, let's say, CH. Right, this is P over 2. This is again P over 2. So based on this, maybe I use this area. So CH, call this tension, which is P over 2 times tangent theta, and tangent theta would be H over 4 HB over 4 divided by H over 2, and from this again you would get T 0.25 P 1 minus HB divided by H. So this is commonly used in anchorage zones. So if you are designing a prestressed element, and this is how you use strut and tie method. For anchorage zone. So this is based on the log splitting example which I shared with you. In practice, we spread the reinforcement. We don't concentrate the reinforcement. The tension which is for this element, so this is T and T, so this is tension element, we always show it at the centroid, but in real application we always distribute reinforcing over a certain distance. Okay, so that is going to be the tie when we start set and tie method. So these are just some light introduction of what is this idealization. So it's nothing but idealization of the stress flow. So stress flows, and you have to see that this is what is required. In the old days, design used to be done by sometimes architects, sometimes some experienced people with capabilities to see stress flow. So this all based on visualizing stress flow, knowing H would be the disturbed region, and creating a logical truss model within that region. So it's all about that. At this point, do you want to add something? I know you have tremendous experience designing members. You do, I'm guessing, also anchorage zones or other similar applications. If you have any comments or any question, we can discuss further.
So Dr. Gunnar, I guess for an anchorage zone for a pre-stressed beam, I think we usually have to put the steel within like H over 4 as opposed to H. So is there a reason that we have to put it so much closer to the end of the beam?
I'll come to that. So that is my example. So I I created that example for you because I was expecting that would be interesting to you. So actually there's going to be two sets of reinforcement needed, right? There's going to be spalling reinforcement needed close to the face, which I think what you are referring to in this region, right, which is pretty close to the base plate. Is it what you are referring? And the other set of reinforcement would be at in the disturbed region. So there's going to be two sets of calculations. So this is only one set, which is the disturbed region part, but the other one I have a full example that to show you once we have some coverage, but that's a pretty good point. I hope that answers your question for now.
Yeah, that's fine.
Any other questions, please speak up at any time. Always my pleasure to discuss as much as I could answer. I would be happy to answer questions. So truss model, Strut and tie model, nothing different than a truss model. So you are creating a truss model which makes sense. That is the requirement with this. So what I should say, cracked concrete carries load by compressive stresses in concrete and tensile stresses in reinforcement. So here I would like to direct your attention to my wording. This is the introduction, right? I'm just starting strut and tie, but I started with cracked concrete. Do you have any suggestion? Why do you think I started with cracked concrete? Why it's cracked? If you have, any suggestion, you can always say. Strut and tie is only for ultimate limit state, so it is not for serviceability. It is not for uncracked concrete. It is for ultimate limit state. So we are going to be dealing with cracked concrete, but we are going to be neglecting the complete contribution from concrete. We are assuming that concrete is gone after cracking, so concrete will carry compression only, right? Reinforcement will carry tension, nothing else. So this is the reason for this. We are always going to be focused on ultimate limit state when we talk about strut and tie models. Okay, so how we would idealize this? So principal compressive stresses would be your struts. Principal reinforcement would be ties. Connections between those two nodal zones or let me fix this because I want to be consistent with these connections between struts and ties would be nodal zones. So typically 3 components, 1, 2, 3 components create a truss model, right? But in reality, definitely the 4th one I want to add reinforcement anchorage. I will come to this later on, but there are 4 components we are talking about when we discuss truss models, which is strut and tie models. So you can see examples. These are struts. This is tie. Usually we use red color for ties, black for struts. You have some angles. This is a structural member. It could be anything, any type of member with 2-point loads. This is a corbel. You can see you have ties, which is solid line, and also you have struts here. This is a continuous beam, so we have ties at multiple locations as well as struts. So we will come to this. This is just a light introduction. So you might have already worked on these before. A couple more example. Definitely these are more advanced, so I'm not recommending anyone tackle these type of openings. So deep member with opening is one of the more complicated type of situations. Again, you can see solid lines represent ties, dotted lines represent struts. This is depth and beam. This is used in bridge infrastructure as well. It's a typical model with ties, struts. This is a footing. It's a spread footing. In this method, there is nothing as uniform distributed load. Again, as I said, only tension compression, no shear force, no moment, no uniform distributed load. So if you have a uniform distributed load, what needs to be done is to convert it to a number of point loads, which is what is done in this example. This is a bit extreme. This would take a lot of time to develop the model, but you can do that. Usually we go with certain idealizations, maybe 11 point loads. I'll come to that later on. So you divide it into a number of point loads and you solve it based on geometry. So you need to solve the truss model to be able to start the process. So this is a nice example. So I would like to think a little bit about load transfer. So there are 2 loads applied, and this load will go here. Let's call this P over 2. P over 2. So, and the left part is slender. Of course, every slender member will have deep regions, but it has a slender region at the middle. So that's what we mean. We call a member slender, means that there is a slender region at the centroid. A deep member do not have that. The deep member has no slender region. This is a completely deep region. So strut and tie model, the logic is based on this. You would, so your purpose is to move this load to the support, right? If you move it like this directly, it is not going to work because the angle would be too shallow. That is a very important distinction with strut and tie methods. You have principal stresses, you have tensile stress. The red indicates reinforcement, so it indicates there is tension which is horizontal. For this one, right, you cannot get compression horizontal, so you want compression to be maximum angle with tension, ideally 90 degree, right? The larger the better. Your upper limit would be 90 degree, but you don't want super shallow angle. It's going to be a horrible mechanism it's going to be inefficient. Tension and compression, two opposite mechanisms. You don't want them to be close to each other, right? So based on this, if you look at any code, there are limitations of that theta. H2 requires minimum 25 degree, which is a super low angle. So I would get concerned if I see 25 degree in my models, because it's going to be, it would usually fail. It wouldn't pass easily if you have that angle. So going with this angle will not pass. It's not going to be an efficient transfer. So what you need to do for this one is to use straps. So go with a steep angle. Again, stress likes big angles, right? So angle is important. Large angle. When I say angle, it is for example, call it this angle, call this theta with this one. So you are shooting your compression with a steep angle, as steep as possible. It's going to make it much better, but now you didn't reach the support point, right? What you need to do is a stirrup lifted up. So the stirrup will only take tension, it would lift it up, and then you would shoot it again. That is going to be the mechanism for slender member, because you cannot really directly send it. Shoot it with a steep angle, lift it up with a tie or a stirrup, and then again send compression, lift up, I hope it makes sense. If you look at certain guidelines, especially in H2O, if you look at the latest version, you will see this figure, and it's going to call this inefficient. The reason for this is that you are doing unnecessary work. The system is doing unnecessary work because you keep lifting that P over 2. Tension here is always going to be P over 2. So P over 2 here, again another P over 2 here, another P over 2 here, right? So my in-class example for this one, think about you are doing exercise at the gym, right? So you lift up some dumbbells and you would move it from one location to another one, right? So if you are taking one step, putting it on the floor, lifting it up again, taking another step, dropping it to the floor, lifting it up again, you are just going to be creating a lot of inefficient work for you. I mean, if you are trying to burn calories, maybe that's what you want, but normally for a stress transfer, this is inefficient because you are really doing the same work again and again. So that is the slender beam mechanism. There is nothing you can do about it. If it's slender, you would need to do this lifting, right, to get good angles. If the angle is too shallow, you will see that it's going to fail. It's not going to be any good for the system. But if you look at a deep element, if you have a good angle, you don't have to do that lifting again, right? So just send it very nice. I'm seeing maybe 45. 45 is a good angle, definitely. If you get theta around 45 degrees, it's pretty good. You are done. Super efficient. You are going to get much better capacity from a deep member. No straps needed. No lifting needed. So for that reason, deep members always superior. It's going to give you more capacity, more efficiency as compared to slender members. Okay. The anchorage, I wanted to highlight the anchorage. If you look at tensions for the system, the tension in the tie will keep diminishing. If you do this analysis, the tension would be maximum in the midspan region, but the tension would diminish as you come closer to the support. So typically you can cut the rebar at the support because tension would be minimal. So that's the slender element behavior. But if you have a deep member, it is different because constant tension. T constant. So you are carrying the maximum tension everywhere, including the support point. For that reason, I highlighted this as the fourth important aspect: struts, ties, nodal zones, and anchorage zones. If this reinforcement is not anchored properly, you are not going to be developing deep beam action. It's not going to work. You would get a big crack at that location, and you are not going to get that capacity. So because of this constant tension, the reinforcement should be anchored from both sides, and we'll come to that. So that's sort of something you have to be mindful, because the member might be deep, but if you don't have proper anchorage, don't consider it as a deep member. Just use slender approach, because it's not going to work as if it is a deep member. So there are penalties. You have to apply those penalties for improper, insufficient development length, and that would really reduce your capacity to a slender element capacity. So that's a really important distinction. So in a deep member, what you need to do is to create a truss model. This is a truss member, and it has to have some area. So what you need to do is to develop that area for that strut, right? Something like that. So this is your strut. And beam has thickness, that's going to be T, and this is your strut width. So this is W, strut width. And let's assume we are living in 1910, a long time ago, and we wanna design this strut capacity. And what we can write down for that capacity: concrete strength times W strut T, this is area. So the concrete strength is pressure, right, times area. That's going to give us the force. That's it. So that's going to be the strut capacity. Of course, you want to factor this, maybe phi C, for safety reasons. So you don't need any code, you don't need any expressions. Your strut capacity would be concrete strength times area, strut area. So that is pretty much what it is. Okay, so that's your strut capacity. Tie capacity would be Fy times bar area. That's it, right? Of course, you would multiply this with it's limit state design, so you have to multiply it with phi s. That's pretty much it. So this is what I mean. There's no heavy calculations involved, and you can do this even without having any calculator. I'm going to summarize it again here using a little bit more formal notation. So struts factored resistance is going to be PR, would be equal to, again, phi C times FCU times ACS. So that is going to be the strut capacity. There is also plus, I mean, we don't do this very often. You have to be really desperate to use the second term. It's not extremely recommended, but you can reinforce struts as if, let's say you have a column which doesn't have enough capacity. What you need to do is to increase the dimension. So that's the natural way of solving the problem, but you can also put more reinforcement in it to increase the capacity. This is that last resort. If you have to use this last resort, you can use the steel capacity for compression. So this is called reinforced strut, which is not very common. So I would add this if reinforced strut. But normally you have this situation. Here, phi c, you know, it's based on the code. FCU would be limiting stress in concrete. Of course, in concrete strut, we are talking about strut. And ACS would be cross-sectional area of concrete strut, which is again width of the strut times thickness. That is going to take place. Now the question should come, why this is not F prime C? Why this is FCU? Because previously I said we use F prime C if we know nothing about any advanced design, but this became FCU, and I'm going to explain what that is in the second page. So this comes from Collins's textbook. It is still used, and you can find it in commentary of H2O. So maybe let's look into this one. F prime C is for brand new concrete cylinder, right? So for you to get F prime C, you need to make a test of brand new, meaning uncracked. Uncracked. So, but when you do set and tie, again, we are talking about cracked concrete, because if you can see the principal stress trajectories in this figure, you can see tension, compression always perpendicular to each other. This is your strut. There is significant tension going on. There is going to be some cracking involved. So your element is subjected to tensile stresses at the same time, and it's going to crack. For that reason, your F prime C would be less for that situation. So if you have concurrent tension applied on the member, which is always the case for diagonal struts, which is this element, this FC2 max would be the limiting stress, which I defined previously as FCU, which is always going to be less than F prime C. So that's the reason why we reduce it to consider cracked condition, right? So the best case situation would be a strut not crossed by any tie. So this diagonal strut do not qualify, because this diagonal strut is crossed by a tie. You can see the tension stress field, but there is a strut at the top which is not crossed by any tie. It's the compression region, compression zone, and it is going to be the maximum capacity, which is not crossed by a tie. In that situation, FCU would become 0.85 F prime C. So that is your upper limit, the best case situation. If it's crossed by a tie, which is a little bit worse situation, it indicates diagonal struts usually. What is going to happen? FCU would be function of theta.
And of course this has to be less than 0.85 f prime c. This is a worst situation, so the best case 0.85. This has to be smaller than that. It cannot exceed that in under any circumstances. So this is simplified equation. Applicable if Fy less than 60 ksi. So you can see how theta affects f prime c. This is what I meant in the previous example. The shallower the theta, the worse the condition would be. Theta is everything for a certain time model. Shallow angles indicate inefficient models. They indicate slender behavior. It's associated with slender members. So that is that theta, as you can see from this plot, significant penalties of your capacity. The multiplier, you might reduce it to 0.4, 0.2 if you have really bad thetas. H2 limits this with 25 degree, which is here. So probably you might get around this number as the worst case situation, but it's a major reduction. So if you get that theta shallow, then you're developing your angle, your model. If you see shallow angles, that's not a good sign, because it's going to have some issues down the road when you come to that check later on. For large thetas, the best one is 90 degree, right, which is 0.85 situation, which is this one. You have 90 degree at this location because it's a horizontal strut. Tension would be vertical if there's any tension. So this shows you really nicely situation. Okay, so this equation has some debates. Practitioners find it to be a little bit too much of a work. For that reason, H2 simplified it. So now what I'm covering is the basic formulations, right? And this is, again, I said I'm not going into code, but I have to give H2 LRFD 2014. I think it's 2 versions before. It's now it's 9th edition, right? This is, I think, 7th edition. So the final version which we are using today has some simplification. It doesn't use this equation. It has some multipliers. So I would come to that. I didn't want to start with that equations because it doesn't give any sense. It looks like some arbitrary numbers. So, you know, in my coverage, I wanted to show you the physical case so that you understand how theta affects your model accuracy. But when I solve examples, I will use the latest version of H2, and you will see how H2 is doing it. Pretty much it for struts. So 2 situations, not crossed by a tie, crossed by a tie, 2 situations. The second one is tie capacity, which is super simple. Again, as I said before, capacity of a tie would be phi s times area of the bar, which is total area, times Fy. That's pretty much it. And but of course you can always do plus tendons if you have pre-stressing, phi p times APS FYP. So this is additional for pre-stressed. Pre-stressing tendons. But other terms are pretty self-explanatory. So the first one is strut capacity, the second one would be tie capacity, and the third one would be node regions. So there are 3 types of nodes, and I'm going to discuss those three types, the best case scenario would be struts and bearing plates. It is going to be 0.85 multiplier, 0.85 phi C F prime C. Truss and bearing plate locations. Crossed by one tie, so if the nodal zone is crossed by a single tie, 0.75. And finally, crossed by more than one tie. .65. And these are called internationally CCC, compression, 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 no tension. CCT, only one tension in this, and then CTT, two tension. This is how these are called. So when we develop a model in the second hour, we would use these in that development. One thing which is additional knowledge, compressive stress limits, also applicable to tie reinforcement. So what we want is a good distribution of the reinforcement. So we don't want reinforcement to be too much concentrated. We want reinforcement to be distributed, and in order to make sure that it's distributed properly, you need to distribute it over an area which is going to be larger than tension tie divided by stress limit. So in my first example, I'm going to check that. So I'm going to check the reinforcement distribution. So this is the second point. So I told you that this is a point H2 did not like very much. It's changed. The second point is this. I will do this so you know it, but in the final version of H2 they removed this. So H2 removed this requirement, citing that there is no data on it. You can always use this optionally when you are checking your design, or maybe you are checking a design based on the previous H2. So you would be able to do that because previous version uses these. So I'm covering really the final two versions of H2 for. So anchorage of ties are another important point. In a deep member, what you need to do is to make sure that you have properly anchored reinforcement. So this situation may not work and you might need some hooks, and we would do this check. In general, hook is needed, but sometimes it's not. If you have enough distance for development, you might get away without any hook. So typically constant tension. In a slender beam, maximum tension would be at the midspan. And at this point, tension would be almost zero, because in a slender member we are using moment diagram concept, right? So your moment diagram for this situation would be something like this. If you do reinforced concrete design, you always show it underneath, which is going to be a plus. This is moment maximum, moment zero, right? So in a slender beam you can just cut the reinforcement, but in a deep beam it has to be properly anchored. Then you check the development. You don't check it at the nodal point. You always check it. This is your nodal point, but typically you have compression coming into the nodal point. So you need to check your bar development. Your bar is here, right? So this is, maybe I use red color. This is tension. So you check bar development at this point, which is at the face of compressive strut, because the compression coming from this direction is anchoring it. So that's the point you need to check. Okay. This is only applicable for bearing areas. So when you are checking bearing plates, if you have available area, so this is your bearing plate, right, and you have some unused concrete which is confining your section, then you can enhance the capacity, because there is a difference, right? So you might have such a narrow member, something like that, and you might have a bearing plate like this. So concrete capacity under the bearing plate will not be the same, because in this situation you have unused concrete which is going to be confining the section. In this situation you don't have anything confining, right? So based on this we are permitted to enhance the capacity based on the ratio of the area, right? So large area divided by small area, take the square root of it, and I think there is an upper limit which is 2.0. I'm going to check this over the break, but I'm pretty sure it's like this. So you can enhance your strut capacity by this multiplier. So multiply by this. So in other words, the multiplier applies to the first one. So if you want to put, you can put that multiplier here, which is applicable to the first term. I don't keep writing it again and again because it's only applicable at certain locations. So then I see typically any overloads, you are checking a bearing plate, you saw it's overloaded, then you come and check this. So typically we don't do this by default. Typically bearing plates passes, but if you have a bearing plate with fails, which is under capacity, then you look, oh, is there any additional area? Then you try to use this to enhance the capacity. But other than that, if the bearing plate passes, you don't have to go through that calculation. You can always use this 0.85 multiplier for the bearing plate. For concrete, 0.7, right? 0.9. So these are the two requirements for H2O. H2O also requires, it's not related to material resistance factors, but I'm going to say that theta should be larger than 25 degree based on H2O requirements. It has always been like this. ACI also requires larger than 25, but 25 is a pretty small angle, so I don't recommend going with 25 degree in your models in general. We need to determine the width of the strut. Thickness always easy because it is coming from the member thickness, so there's no calculation involved, but the width depends on the anchorage condition. So it depends on the bearing plate size as well as the angle, right? So for example, in this case, if you are trying to determine this width, what you should do is to come to this handout and go with this one. This is that situation. Strut is going to the bearing plate. There is a tension tie, exactly this situation. So what you need to do is LB sine theta. LB is, it could be a column, right? Or it could be a base plate, whatever is supporting it. It is this dimension in that situation. So LB times sine theta, which is that major angle, plus HA, height of your tie. So each tie will have a height, which we would come to that. That distance times cosine theta. So that's how you would get it at this location. What about at the top? So let's say you want to get the width. It's different. At the top, it's smaller. You are going to be coming to this handout and do the same thing. LB, which is the bearing plate length, sine theta, plus HS, which is strut height, which we will determine cosine theta. So that's how you would get it, right? This situation, I have an example for that. This only happens if you have UDL. So let's say you have a beam, you have some UDL, and the UDL is joining, UDL is coming to the support, right? This is your fan region, and in this situation we are only going to be checking the critical strut. Always the critical one is with the smallest angle. Shallowest angle would be the critical one. It's going to be critical not only because of the angle, but also force will be the maximum. If you do the statics truss model, if the angle is shallow, it's going to be losing twice, both from strut and tie perspective as well as from the force perspective. Both forces largest if you look at all these forces, and capacity would be the smallest. So check that one. This is the strut width. We would use this. I have an example to complete that. This is another situation. Even if member is a deep member, we sometimes need to use stirrups. If you are using stirrup, which is sort of, you are supporting with a stirrup, right? So it's sort of an imaginary bearing plate here. You don't have a bearing plate at the bottom, but you have ties lifting it. So you need to determine that effective length. So we would be using this. So these are universal formulations used in HTO, used in Canadian code, used in other jurisdictions as well, because these are all met dependent, except this one. This has this assumption 8 times bar diameter. So it determines the effective length using 8 times bar diameter. It is a little bit based on assumption. Canadian code uses this, HTO also uses it. So 8 times bar diameter would be the number that we would be using. Crack control reinforcement. So this is another critical aspect. Crucial. You have to provide crack control reinforcement. Strut and tie method is a lower bound theory. What does this mean? It is guaranteed to be conservative in all cases. So I should say always conservative. And there is an important fine print, provided that you have crack control reinforcement, because this really holds the integrity of the member. Provided that you supply crack control reinforcement. Extremely important. And I will show you experimental results. If you don't have this reinforcement, the member fails before reaching the capacity, because it's a really deep member. You provide reinforcement only at certain locations. If you don't have crack control reinforcement, you suddenly have a crack at the web and the member fails. So it is such a critical aspect. We have to provide. H2 is a little bit on the higher end. Typically, other jurisdictions, other countries require around 0.2. but H2 requires 0.3%, which is good. So vertical directions, you have to provide 0.3% or more in the vertical direction. So if you look at this, vertical direction would be, it's the strap direction. This is rho V, vertical direction. The horizontal direction is the same percentage. And horizontal one would be these ones. Okay, so you must have crack control reinforcement. If no, penalties apply. I'm not covering it yet, but I'm going to do examples with those penalties. Significant reduction in capacity, so that's what will happen if not penalty multipliers, which is going to be 0.45, applies or apply. If the member is thick, you need to provide something additional inside, so you can find details from H2. When to use Strut and tie method? What do you think about this? Do you have an answer?
When you have deep beams.
Yeah, absolutely. That's the answer. When you have something deep, use it. Can I use it if it's slender? Is it possible? Or is it going to be a big mistake if I use it for slender members?
No, you can use it for that too.
Absolutely, absolutely. So that's a really good answer. Of course, deep members you have to use this, but there's really no major issues if you use it for slender elements as well. But of course, best to use, or I should say most benefit. So you would get the best or the most benefit out of using this benefit will come when analyzing deep members. It could be a wall, it could be a pier, it could be a beam, anything. What is deep? I want to clarify that. How do we quantify? So previously I said section depth is H. You go H from here, H from there. If they overlap or if they intersect, it's completely deep region. So it would make the aspect ratio 2, right? If this is H, if this is 2H, it's going to be a deep region entirely. So 2 is the magical number. So if you have that 2 situation, depth to shear span 2 would make it a deep member. I would refine this a little bit more. So H, I said previously H, but now typically H is effective depth, because concrete behind, underneath reinforcement do not really work. So typically for our practice, H is effective depth, right? So this is D. If this is 2D or less, it's going to be a deep member, right? So call this A. So A is called shear span. So shear span to effective depth is smaller than 2 or even 2.5. This is transition region. So H2 would say 2 because that's the lower bound. It is also fine, if you consider a member deep for ratio 2.5. This comes from Michael Collins's textbook. It's also in the code. I think the Canadian code has this in the commentary. there are two methods plotted. So on the vertical axis, it's capacity of the member. The larger the number, the larger the shear capacity. On the horizontal axis, it's shear span to depth ratio, right? These plots indicate different methods. So stand time method prediction is this one, solid line. Sectional model prediction, which is based on moment shear, which you use it on a daily practice, based on the dotted line, right? So these are the two calculation results for different shear span to depth ratios, and the dots indicate the real behavior from experiments, right? So if you look at shear span to depth ratios larger than 3, your sectional method performs very well, right? So this is the slender region, less or larger than 3. So, you know, the ratio, you know, cut this at 3. If it is larger, it's slender. So really, there is really not a benefit of using strut and tie for slender regions. Just use your sectional model and you would be pretty good. If you use strut and tie, you would be conservative. You would be under predicting the capacity for slender members. Again, being conservative is good, but maybe not something you want for economical reasons. So again, you know, for slender members, sectional method would work the best, right? 2 to 3 transition zone, as I said previously, but less than 2, sectional method will really give you a fraction of the capacity. So you can still use the sectional method. It's not valid, but it would still give you something, some result. The real case, the real capacity would be always larger. So the deeper the member, the discrepancy will increase. So if you have shear span to depth ratio 1, and if you use your software, which is based on sectional model, and if you get this capacity, if you use strut and tie, you might get 4 times larger capacity. So the benefit would be tremendous for deep members. Deeper the members, bigger the gain, right? So 1, aspect ratio 1 is good. That's a deep member for sure. 1-to-1 aspect ratio. So this is D, that's D. So the point load should be pretty close to the support. And in that situation, the benefit, you would be really getting three and a half times for this one, 3.5 times more capacity. If you use the right method, which is strut and tie. So anything less than 2, definitely you should use strut and tie. 2 to 3, it's up to you. It depends, you know, what you have available at that time. If you have sectional available, use sectional. If you want to do strut and tie, do it. But less than 2, definitely. Even for 2, I mean, if you want to use sectional, use sectional. You would be under predicting the capacity, but it's not going to be a huge under prediction if you look at the under prediction. Still, you can use sectional, but you know, your error will increase if that ratio reduces. I hope this is clear. I always check that ratio that sets my expectations. If I see a pretty small ratio, my expectations are high. I always recommend you still use your sectional method. You can still get the capacity from sectional, and that would a little bit cross-checking and check how many more times you got capacity from strut and tie. So that might be a way of checking your answers. This is that. These are important topics. The other one is, I get this question a lot, because you can create more than one model for the same problem, and people asking how that's possible. Say multiple valid, of course I'm talking about valid STMs can be developed for the same problem. However, each model will have a different capacity. It depends how refined your model is. So you might get different capacities. If you really nailed the model, if you refined it, you might get larger capacity than you get from a coarse model. So I should say each model will have a different capacity. I don't mean radically different. There's going to be some difference, but sometimes they are pretty close. So I would say more refined models will typically have larger capacities. I would really like to emphasize this discussion applies to correct models, because I have seen a lot of models which are not valid to begin with. So this applies correct valid models. So you might have more than one correct solution for the same problem. Here you can see A and C the same problem, same span, UDL. This is idealization with 2-point lows. This is the coarse model. Coarse model is going to be simpler. You can finish this maybe within 1-2 hours, but this one would take more time. This is a refined model for the same problem. If you are in a rush, you can always use a coarse model, get a ballpark capacity, but if you need more refined results, you can always do the second analysis using a refined model. So in this model, this is going to be the one which would govern. So we are not going to be checking everything. Only the shallow strut with that shallow angle would be checked when we check diagonal struts. This is a foundation. Again, we would only check the shallowest angle strut, which is this one, when we check diagonal struts. This is again two different approximations. The second one is refined. This is good enough in general. I mean, in this situation, this is more obvious because it is UDL and it's really clear that this is a little bit coarse model. You are just idealizing it one strut. But in this situation, the difference is much less, right? So the capacity difference will not be too much, but the effort would be much more in the second one. So for this situation, for example, I would recommend refined model if you have overloads. Let's say you are not able to pass this one. If you do the refined model, maybe you can optimize the capacity by 15%, 20%, right? But this is going to be, it's an indeterminate system. It's going to be definitely much more work. You would be determining the load proportions in this system. Also, using crack control reinforcement is usually last resort because crack control reinforcement is nothing major. It's not going to lift up big forces, but sometimes you need that. Sometimes you might need this one, usually not used. I should highlight that. That is pretty much it.
Could you maybe comment like on these uniform load examples there, like what the shear span, how you calculate the shear span on that?
Typically, you consider point load applied at the midspan. So when you calculate shear span, if you have a UDL, you just replace it with a point load. So your shear span A would be this distance. Maybe some of you used Strut and tie before, maybe you developed some models, and maybe some of them gave you really hard time because you might find yourself in that situation. Sometimes some models really stubborn and they don't want to pass, and you might end up spending good time on it. All right, so always start with the easiest one, make sure that it passes, and then you can refine it later on. I don't recommend starting with a complicated model, which may not even be necessary.